The approach to structures that we've talked about so far is totally general. It works for any structure that's statically determinate. But it does produce a lot of equations and a lot of variables. And so, in a very specific set of cases, you can reduce the number of equations and variables a lot. And that is when you can treat a structure as a truss. So here I'm going to be talking about the truss simplification. And if you only get one thing out of this lesson, this is the one thing that you need to remember. This only works for structures with very specific properties. I guess we'll call it one very specific property. And that property is that every member is a two-force body. Okay, so I'm going to start by talking a little bit about what a two-force body is and why that can simplify things so much. So, okay, here are two-force bodies. And two-force bodies are only important when you're in equilibrium. In statics, we're always in equilibrium. That means there's no acceleration of the body and no angular acceleration of the body. So this is two-force bodies in equilibrium. So in statics, two-force bodies. Okay, so if you have a general object, let's say it looks like this. I'm going to move this down a little. And let's say that the only loads acting on this body are two forces, and those forces are going to act at the two, places where we'll imagine like joints being if this was a structure. Okay, so we know this is a two-force body. Let's first think about what would happen if these two forces, were just like random direction and magnitude. Well, in that case, since these two force vectors, if you added those up using vector addition, you would get a vector that is non-zero. That would produce an acceleration of this body. Okay, so I'm going to erase these. But the key thing to know about that is since we're requiring that there's no acceleration, because this is an equilibrium, the only way that that's possible is if these two force vectors add up to zero. In other words, these force vectors have to be equal and opposite. If they're not equal and opposite, they add up to something non-zero, and then you get an acceleration. And that's not possible if it's in equilibrium. Okay, so now let's consider the possibility that they're equal and opposite, but going just in some random pair of directions. So there's one force. The other one has to be equal and opposite. Try to get it looking parallel. That's a little better. Okay, I don't know. Okay, so those are the same magnitude, opposite directions. But notice that this produces a couple, and that would make this thing rotate. So if we're going to assume that there's no angular acceleration, the only way that there's no moment produced is if these both have the same line of action. So they both have to act along the line between the 2 points where the forces are applied. And there are 2 possible ways that that can happen. It can happen if they're opposite each other, going away from each other like this. Or it can happen if they are pointing towards each other along that same line like this. Those are the only 2 possibilities. Okay, so let me draw one like this. Try to draw basically the same body. One like this. Those are the only 2 possibilities. And so since we know so much about what's allowed for these 2 forces, for a 2-force body in equilibrium, we can take advantage of that when we do the structure calculation. Okay, so let me finish writing the text. No angular acceleration requires that these have the same line of action. In other words, they're equal and opposite, and the 2 forces are either pointing exactly towards each other or exactly away from each other. What's required in a structure for the members to have this? So what this means in a structure is, first of all, none of the members can have weights. That's a pretty big one. I mean, obviously everything has weight, but there are cases where the weight is so small compared to the other forces that neglecting the weight doesn't affect the problem significantly. So there has to be no weight to the individual members in the problem that you're solving. What that really means is that the weight is negligible and you can get accurate results without putting the weight in. The second requirement is that all external loads have to be applied at the joints. There can be no external loads applied, like, say, at the midpoint of a member. Then, since there are a couple that relate to the fact that the only loads are 2 forces, well, then you can't have any joints that produce couples. The only joints you can use produce only forces. So the members themselves are connected by either pin joints in 2 dimensions or ball and socket joints in 3 dimensions. And then third, there can't be any couples, no couples can be applied to the structure in the reactions with the ground. Okay, so no fixed joints, no pin joints in 3 dimensions that where you're relying on the couples being applied. Um, Nothing like that. Okay, so let me draw an example of a truss, and then we'll go through these requirements, and I'll sort of explain how we've figured out that this thing can be treated as a truss. All right, so let's say that we have this structure. There's a pin over here at the lower left, and then all the members are connected to each other by pin joints. Um, so there's, imagine little dots at all these connection points. Why did I do so many? Okay, and then let's say that there's a roller here that I say connected. It's resting on the ground, and then there are external loads applied here and here, and importantly, we're not going to assume that there are any significant masses to these bodies. So the problem wouldn't give you any masses for these bodies, and so we'll say neglect the weight of the structure, the weights of the individual members as you do this. Okay, so let's just go through those 4 requirements that I have here, what this means in a structure, and we'll make sure that this meets all those requirements. So first, is the weight negligible? Yes, it says to neglect the weight. So we're good there. Second, all external loads, are those applied at the joints? Yes, so external loads here would be, well, we have reactions connecting it to the ground at the lower left and the lower right, and those are applied at joints. And then we have the 2 force vectors shown both acting at joints. So yes, we have this. The members are all connected by pin joints. This is a 2-dimensional problem. Although, one thing about trusses is you can do these problems in 3D just as well as you can do them in 2D. The other structures that we're dealing with, we've only talked about in 2D. And yes, they're all connected by pins. And now let's go to the reactions. Do either of these reactions, of these joints connecting it to the ground, apply couples to this structure? No, this is a pin joint, so it applies a force vector. This is a roller, so it applies a force with a known direction that's perpendicular to the ground toward the body. So this holds, and now we know, hold on a second. I'm back. And now we know that we can treat this as a truss, and we can use the rules for solving trusses, which again, like I said, can save us in cases, can save us a lot of equations and a lot of variables. So here's how you go about solving a truss. So in a structure that meets the truss requirements, we're going to treat every member as a cable. So we're going to act like every member is just in pure tension. Um, if the tension for one of these cables, one of these bodies, so I'll put cable in quotes, comes out negative, that just means that the member is in compression. So, think about in this body, um, if you think about what would be happening to this member where my cursor is um, over on the right side, that downward force would have the tendency to try to squish that member. And if it was a cable, it wouldn't be able to support that compression. That's why cables can only allow positive tensions. But when you're talking about um, sometimes these are referred to as slender rods. When you're dealing with um, a solid body, it can sustain tension, but it also can sustain compression. It won't allow itself to just be accordion squished. Okay. And so if you get a negative answer for a tension, that just means that the body is in compression instead of tension. Um, and the way you're going to go about this is you're going to isolate the individual pins using Newton's second law. And the reason we're not going to use the moment equation, so I'll say Newton's second law only. We're not going to use the moment equation because we're thinking of these pins as particles. And remember, when we did particle statics, we didn't use the moment equation. Okay, the last thing I want to say here is you can always, it'll always work out the number of equations and the number of variables if you isolate every pin in the problem. Sometimes, though, if you're clever, not always, but sometimes you can figure out a way to solve for these tensions. I'm doing air quotes on tensions, cable tensions, in each one of the members without isolating every pin. And I'll show you that in the example. Sometimes you can find the tension or compression in each member without isolating every joint. You're going to have to isolate most of them, but sometimes you can get away with leaving one or more out. So sometimes you can do it without isolating every joint. Okay, so now with this approach, I'm going to go through an example. So let's say that we have a wall here, and we have a pin joint there connected to a member. And then we have another member there that's connected to a roller. That's supposed to be a roller that's pushing against the wall. And then there's a third member there. So we have a pin joint at the top. At the bottom, we have a roller. And this member makes an angle of 30 degrees with the horizontal. And then let's say there's a 500 Newton force here. Well, it turns out maybe surprisingly, the lengths of these members in this case don't matter, since I just gave the angles. And so I'm not going to give lengths for these. It's true no matter what those lengths are if that angle is right. And we are going to neglect the weight of these members. And we want to solve this structure, which means we want to find the external loads, all the external loads acting on each one of these bodies. All right, well, let's think through the requirements and make sure that we can, we know that we can use the full general method to do this. But think for a second about how many equations and how many variables we would get. We have 3 bodies. We'd have to use Newton's second law and rotational Newton's second law for each one. It's in 2D, so each body would give 3 equations. So that's a total of 9 equations for 9 variables. And that's a lot. But let's think if we can use the Truss simplification here, because that can cut down what we need to find a lot. So first, the individual members need to have no weights. The weights have to be negligible. And that was provided in the problem. So far, so good. Second, the external loads have to be applied at the joints. The connection to the wall is at a joint. The other connection to a wall is at the joint. The 500 is at a joint. So that requirement is satisfied. The members are connected by, this is 2D, so they have to be connected by pins. And I don't know if I said that, but that's the idea here, is that everything is connected by pins. And then fourth, the last requirement is the reactions with the ground can't apply any couples. Well, this is a pin joint with the ground. That doesn't apply any couples. This is a roller with the ground. That doesn't apply any couples. And so we're set. We can use the Truss simplification for this. And let me label these. I'm going to call this joint A, B, and C. And then for the members, I'm going to call this 1, 2 on top, and then the diagonal one will be 3. And so remember, the idea is we're going to isolate the joints, and we're going to treat each member like it's a cable with a tension. So I'm going to start by drawing a free body diagram of the joint A. And that's just a blown up view of the pin. So what loads are acting on that pin? Well, member 2, which we're thinking of as kind of like a cable, is going to be pulling the pin this way. So this is going to be the force 2. Instead of using T, I'm using F, just to remind us that this can come out to be positive or negative, unlike a real cable tension. But the default direction is always going to be tension. And then member 1 is going to be applying a force this way. And then a pin joint applies a force, an unknown force vector. And so I'm going to call this reaction force RA. Since we're treating this pin like a particle, we only have Newton's second law. So I'll write that as RAX, RAY plus 0, negative F1 plus F2, 0. And if we write this as our first two equations, that says RAX plus F2 is equal to 0. And the second one says RAY minus F1 is equal to 0. And that's it. One joint, two equations. And now we'll go to a free body diagram of the joint B. And again, I'm going to, my isolated body is that pin that's connecting the roller and connecting those two members together. And we'll think about the loads that are applied. Well, first, we're going to assume that member 1 is in tension. So notice that this time that force F1 would be going this way. We're just following the rules of cable tensions, parallel to the cable, away from the body. So our F1 goes this way. We also have an F3 going this way. And then we have the frictionless contact or the roller contact with the wall. The rule is perpendicular to the surface toward the chosen body, and I'll call that RB in honor of RB's roast beef. And then we'll go to Newton's second law. So RB 0 plus 0 F1 plus, now we have to use a unit vector for this one. We're going to use that 30-degree angle. We'd have F3 times the cosine and sine of 30 degrees. So this is 0.866 F3 and 0.5 F3. And we get a third equation that says RB plus 0.866 F3 is equal to 0. And then a fourth equation that says F1 plus 0.5 F3 is equal to 0. And then we'll go to the last joint, which is C. So free body diagram of the joint C. We have member 2 pulling to the left, member 3 pulling diagonally down and to the left. And then we have that 500 Newton force acting on this pin at C. So we have F2 this way, F3 this way, and 500 Newtons this way. So Newton's second law says negative F2, 0 plus, now we have to use a unit vector here, and you could use 210 degrees, 30 degrees counterclockwise past 180. but this will come out to be the opposite of what it was in the last case. So this is negative 0.866 F3, negative 0.5 F3, plus 0, negative 500 is equal to zeros. And so we have a fifth equation that says negative F2 minus 0.866 F3 is equal to 0. And a sixth equation that says negative 0.5 F3 is equal to positive 500. Okay, so now that's our system. We have 6 equations. Hopefully we should have 6 variables. Let's count them and make sure. We have, so first we have the tensions F1, F2, and F3. And then we have a vector variable, RAX and RAY. That brings us from 3 to 5 variables. And then we have this scalar variable RB bringing us to 6. So we have 6 equations and 6 variables. Well, one more thing, if all we want is the external loads on the bodies, notice that our 2 equations, 1 and 2, introduce 2 variables that we're not interested in. So we could, and they don't show up anywhere else, that RAX and RAY, they don't show up in equations 3 through 6. So in fact, we could throw away equations 1 and 2 and just solve this as a system of 4 equations for 4 variables. So now we're down all the way from solving a system of 9 equations for 9 variables, if we use the full general approach, to a system of 4 equations for 4 variables for the Truss approach. I mean, I can't, stress enough that, of course, you have to remember that this is only applicable in very specific cases. But that's a pretty nice advantage to using the Truss simplification in this case. Okay, so if we just solve, if we think of 4 equations, that's equations 3 through 6. For the 4 variables that show up in those equations, which are F1, F2, F3, and then RB. What we get is that F1, I'm going to spare you the, writing it out as a, well, let me do it. Why not? You can fast forward if you don't want to see it. Okay, so here's the augmented matrix. We have 4 equations for 4 variables, so we're going to have 5 columns, and we're going to have 4 rows. And these are the equations 1, 2, 3, and 4. And then the variables, I'm going to go in the order F1, F2, F3, RB, and then the constants. Well, 1, 2, 3, 4. I mean, these are, the equations really are 3, 4, 5, and 6, the way I have them listed here. But okay, for equation 3, RBs we have 1. F3s we have 0.866. Everything else is 0. For equation 4, F1s we have 1. F3s we have 0.5. Equation 5 now, F2s we have negative 1. F3s, we have negative 0.866. And then the last one, F3s, we have negative 0.5. And for the constant, we have 500. In order to get non-zero values for these, you always have to have at least one thing in the constants column, so that 500 was necessary there. And what we get here is F1 is equal to 500 newtons. Since that's positive, we know F1 is in tension. F2 is positive 0.866, meaning that's also in tension. F3 is negative 1,000. The negative tells us that that member is in compression. And then we also have an answer for RB, which we don't care about, but we needed to get it to solve this system, and you get positive 866. Okay, so to solve this problem now, you need to express these members with all their external loads. I like to do that on free body diagrams. So let's think of each of the three members as a free body diagram. So member 1 is that vertical member. And our answer tells us that it's in tension of 500 newtons. So tension means that these forces go away from each other, and they're equal to 500. Member 2 is the horizontal member. Positive 866 means it's in tension, and these tension values are 866. And then last, the free body diagram of member 3. That's the diagonal one. This is in, it has a value of negative 1,000, which means it's in compression. So these two forces go towards each other, and they have a magnitude of 1,000. And so if you have a structure that you can simplify as a truss, this is the approach, and this is the answer you get, the external loads on each one of those bodies.